Okay. You should check this like I said again, because I uploaded the chymotrypsin mechanism written out much nicer. It looks much nicer. It's not in my like annoying scrawl from, it's not like my annoying scrawl in red and stuff, and it has all the steps like nicely written out. Okay, so serine proteases. We'll just take a minute and we'll just walk through it again. Okay. So serine proteases have the catalytic triad. So that means they have catalytic triad comes from the fact they have 3 active amino acids. And if you're drawing, yes, Paige. Okay. No, so that's a good question. So most proteases are going to have multiple amino acids that are going to kind of feed on each other. On Thursday, we're going to see an example of a catalytic dyad. But there are other proteases out there where some of the amino acids might be switched up very slightly. And so this is and we'll talk about this in class 2, but when you're thinking about exam questions for enzymes, and you'll have an example of this on your enzyme quiz, is you're going to be having to give a situation where I'm going to give you either a real or a fake enzyme. It's going to be like one of the proteases that we covered in class, but something's going to be a little bit different. And so you're going to have to use your logic to figure out what type it is, and then figure out what the mechanism will be based on the substrates and co-fat, co-whatever that I give you. And so serine proteases is one type. And so if it's a serine protease type mechanism, it is always going to have 3 amino acids. One is going to be pulling on the molecule that's going to be acting as an acid base. And the other, that acid base is going to be deprotonating the one that's going to be doing the nucleophilic attack. Yeah. Not necessarily. So, let's look up trypsin. And I'm totally cool with this being like informal. It's not like last time. This is like cool ass questions time. Okay, let's see trypsin. Let's look up trypsin because it's. Let's see. Let's see what I'm sure there's a catalytic mechanism going on there. Can you repeat your question?
I guess I'm just confused, like we like the serine protease, don't we like do it on contract?
So trypsin and chymotrypsin are both serine proteases. But it's more going to be like, I'm going to tell you what's in the active site, and then you're going to have to figure out. So like, based on the active site, does it look more like a serine protease, or does it look more like an aspartate protease? And those are the types of things. We really have to see the other one first before we have an example. But the quiz that you're going to get, and then you'll get another opportunity to practice on the exam. I have another opportunity for I'll post when I post the exam from last semester. You'll get another attempt at a clean slate to practice. Okay. All right. So serine proteases, again, they're characteristic because they have a catalytic triad. So if I tell you an enzyme has a serine, histidine, well, so let's say it has like a serine, okay, has a serine, has going to have a histidine. Okay, I always misdraw histidine, and then I feel like a complete bozo. Oh, yeah, I'm sorry, guys. My histidine is just ridiculous. I'm so sorry. Okay. And then if we have, okay, aspartate. Okay. Okay. So aspartate, again, I already told you. You have an enzyme that has 3 active set amino acids, a serine, histidine, and aspartate. You're going to be like, oh, it's going to look exactly like chymotrypsin. That's your clue. Where if I was like, oh, it doesn't have an aspartate, it doesn't have an aspartate, like it has a glutamate. And you're like, and then you go and you draw that out. And you're like, huh, what does that look like that I already know? Oh, it looks like a serine protease. It's just I added the carbon onto the aspartate to make a glutamate. And so then that would kind of be like their glue, and then you would have to go and reconstruct, if that makes sense. So that's the kind of skill I'm wanting you to be able to predict what something would look like in just a slightly different situation. So in this case, the clue is I have one enzyme that can act as a nucleophile. I have an enzyme, and then I have one amino acid that can act as a nucleophile under the right conditions. And I have two amino acids here, one that can act as either an acid or a base at physiological pH. And then one that's it's going to be deprotonated. And what can we do when we're deprotonated? So in theory, I guess you could make an argument that glutamate could be a nucleophile, although I wouldn't necessarily think it would because it's a little bit bulky up there. I think it's a little too bulky to be acting as a nucleophile. Excuse me. But the combination that you have histidine and glutamate together should be a pretty good clue that it's going to be a serine protease. But yeah, especially like the histidine. The histidine is huge because the histidine is able to waffle back and forth between the two. And because you have two amino acids on your side chain where they can talk to each other because it has resonance, because with the double bonds and the way the orbitals on the atoms are with the lone pair electrons, and that by pulling on one, you're talking to the other through those double bonds. So that's your big clue there, is the fact that there's three. Or you might be in a situation where even if you just have serine and histidine or something like that, in theory also you probably could make it work. But yeah, that's clue number one. And so you're really trying to think of, with the properties of the amino acids I have, what kind of a reaction am I going to be doing? Am I going to be doing a nucleophilic attack like we see with this? Or am I going to be doing the method that we're going to see on Thursday, which, spoiler alert, if you had your slides, it's an aspartate protease. It's not actually going to be making a direct attack itself because, again, when you think about aspartate, it's got a carbonyl on it, and carbonyls aren't great at doing nucleophilic attacks. So it's going to be using water instead as a nucleophile. So it's going to look like step 3 and 4 of the reaction, except without the covalent intermediate. But no need to spoil that. I'll leave that for Thursday. Okay. So we have our catalytic triad. I'm just going to erase this because we're still doing aspartate. And everyone in theory can get the same information because everyone can watch this video. So that negatively charged oxygen can pull on that proton on the other nitrogen. And there's some mechanisms that actually have it deprotonating, but I was taught that it just pulls on it. That's how we're going to write it. And then that's going to make the nitrogen on the other side of the ring that has lone pair electrons more basic. So it's going to make it a stronger base. And so, because when that oxygen is pulling that proton away, it's concentrating those electrons onto the ring. And so it's going to want to give away some of that electron density. And so that's how that the lone pair nitrogen electrons are going to be able to deprotonate serine. And again, remember, this is a special serine where the pKa is approximately around 7. In this case, the pKa of serine is almost out of histidine. Because again, we talked about pKa's, we memorized them to give us a baseline, but proteins can manipulate the environment around an amino acid to alter its pKa. Even to a point where you can make an amino acid that's not supposed to be deprotonated. You'll also see this with cysteine, although cysteine is actually like 8, not 13. Okay. So, do you guys want to walk through the mechanism step by step? You want to see it again? Feeling good? Not wasting time? Okay. Do you have any more questions, Paige? Yes. The pKa for the catalytic serine in chymotrypsin is around 7. Yeah. That's the level that you need to know. What's that? The proteins are around the amino acids that are next to them, that are next to that amino acid, and then the ones that are like close in space are gonna pull it way down. Okay. But yeah, and serine pKa is low enough that it can do that. Like you're not gonna see this happen with like a valine, right? Or even like you're not gonna see a deprotonated or you're not gonna see like a deprotonated asparagine. But oh, this is the wrong charger. Yeah, you'll definitely see it. Right, and so the conjugate base of serine, like it can carry a negative charge, just not great. But it can carry a negative charge better than an NH minus. Is what boils down to. Like like alcohols aren't great conjugate bases. They aren't super stable, but I mean they're stable enough that the pKa of serine is still technically within the pH scale. So yes. Okay. All right. So again, this is chymotrypsin. So we're going to be cutting after phenylalanines. So we draw out our peptide. But I'm not gonna do N to C. We're just gonna do R. Oops, or we can just erase, put it on pan and get confused. We have R. Can you hand that page? Do you have any lingering questions? Okay. Alrighty. Thanks for coming by. Okay. All right, so go up. NH. Down. Oops, did I do too? I think I did too many carbons there. Nope, not if we connect that. We're good. Okay. Double bonded O. R prime. No. No. NH. I hate it when you guys get examples of how I'm not perfect. I like to live in the myth that I'm perfect. Okay. All right. Okay. So the aspartate. So we've got the peptide, my very crudely drawn peptide, because I won't say I suck as an artist because that's not true, but I definitely suck as somebody who draws. So the aspartate is pulling on the histidine. The histidine acts as a what? In what we call this type of catalytic strategy, where the histidine deprotonates the serine. Okay, base, yes. But what's the type of base? What's the basic strategy utilized by proteins called? General base. So, yes. So histidine acts as a general base by deprotonating. And then, now serine is here, and it's all dressed up with its electrons and nowhere to go, except it does. So okay, so then in serine, it turns out when you have an oxygen attached to a bunch of carbons, oh, shut up, Siri. I thought I disabled you. Okay. All right. I better be careful. Who knows what Siri might do to me in my sleep. Okay. So serine, so it turns out, so some nucleophilic molecules or good nucleophiles are molecules that are small. They're not bulky because this is literally going to be an SN2 reaction where you're going to have that atom come in and attack the carbon, and it's going to have 4 things in an intermediate, and then it's going to have 3 again. 3 constituents. And so in order for the nucleophile to attack there, it has to be relatively small. Again, we don't want aspartate in there because we got that carbonyl oxygen hanging off. We don't want histidine because it's like a 5-membered ring. It's not going to be able to fit. But serine, it's small. I like to think of nucleophiles in this case being like a small concentrated ball of electrons. And Again, the reason that makes it a really sucky conjugate base, which makes it not very acidic, is what makes it relatively nucleophilic, because it wants to not have that negative charge on it. So those lone pair electrons are going to make a nucleophilic attack on the carbonyl oxygen, or carbonyl carbon. And so why is that carbonyl carbon a good candidate for a nucleophilic attack? That's true. Yes, that is absolutely true. The electron density has somewhere to go. But the fact that the electron density has somewhere to go is intricately tied to a name that we have for the electronic nature of this atom. So we can think of it as being the opposite of a nucleophile. That's electrophilic. So because that carbon, take a look at that carbon. It has 2 bonds to an oxygen and 1 bond to a nitrogen, or 1.5 bonds to an oxygen and 1.5 to nitrogen, depending on how you draw that. And keep in mind that one of the resonance structures for that is a positively charged, there's charges going on. It's technically zwitterionic in a certain state. That carbon is getting all kinds of electron density pulled away from it, which makes it electrophilic and makes it really happy to receive those electrons. And that wouldn't be the case if we didn't have a double bonded L. The electrons will go up. And then if we do our next step, okay, we'll just draw it down here. NH. Sorry, but the phenylalanine kind of looking like crap. O minus. And so here, you're going to see why. We talked about why histidine wouldn't work. Even from the perspective of trying to draw this out, you could see that like a histidine just isn't going to fit in there very well in 3D space, especially if you got that big bulky phenylalanine there. Right, so we have our histidine. Okay. And then I apologize if I misdrew the histidine, but I think we're okay. Okay. All right, so the aspartate is pulling on the histidine. Still, the histidine is protonated because it stole the proton from that serine. And now we're in this phase where the oxygen has the electron density up on it. And as Alex alluded, it has to go back down. It can't stay up there forever. Although, what does the enzyme have that's going to let that oxyanion form and actually hang out for a little bit? Anybody know? Pardon? What are you saying, Alex? Okay. All right, let's look up at a picture. Okay. Here we go. Okay. So if we look at the active site of chymotrypsin, okay, so this is the first step of the reaction where the serine is making a nucleophilic attack on that carbonyl carbon, even though it looks like it's attacking that bond there, it's not. You'll notice that we have 2 backbone nitrogen protons that are like interacting, they look like they're hydrogen bonding, each hydrogen bonding with a lone pair on that oxygen. But when the negative charge goes up on that oxygen, they're going to stabilize the negative charge on the oxygen. And so this is an example. So this is an intermediate that it's in theory going to be stabilizing, but the transition state of the reaction is probably going to look a lot like that intermediate, where you have that oxyanion formed. And so this is an example of transition state stabilization, is that the enzyme has positioned in this active site these backbone amine protons that are going to stabilize the oxyanion in the transit in both of the tetrahedral carbon intermediates. So, if you're on the exam and you have an example where, like, provide an example of transition state stabilization, going all enzymes stabilize a transition state is not an example of a concrete example. That will not get you, that'll get you a point or two. That'll get you maximum half credit, okay? This is an example. You don't have to draw it, but you have to say, like, enzymes can form oxyanion holes, specifically chymotrypsin as an oxyanion hole. That's the type of thing I'm looking for. And like I said in class, if you have the choice of talking about one, the one to talk about is probably not proximity and orientation. Just gonna put that out there because that one is a little bit hard because all enzymes kind of inherently do that, but we don't necessarily see an example of that. Okay. All right. Minus that one down. Okay. So we're back to our intermediate. Okay. So we know that the electron density can't hang out up there on the oxygen. So it's going to want to collapse down and remake that double bond. But when that happens, how many things do we have bound? Will we have bound to the carbon? 5. Okay. Does carbon like having 5 things bound to it? No, carbon hates that shit. Okay. So one of those things is going to have to leave. Okay. So if we go through and we try to make things that leave. So what would happen if the serine left? What products would we have? And ain't nothing gonna happen. You're gonna start right back where you started. So the serine can't be what leaves there because, well, partially you're gonna be back with that unfavorable negative charge on the oxygen, right? For one. Which, I mean, it could pluck it off the histidine and it will be fine. And in theory, a little bit of that might happen, but that's not going to be the productive reaction. Okay, so let's say we were to break this bond. If we were to have this bond, that means that we would have, oh goodness, I can't do the math, we would have a negative charge on that carbon. Does that look like it's a good thing? No. We don't, it's not going to happen. So that leaves us with the bond breaking being on the nitrogen. And so that bond can then pluck the electron density from that nitrogen carbon bond, can pluck off the proton. The electron density goes back onto the nitrogen. And then what we get is we have our protein or our peptide substrate is literally sliced in half. And it's sliced in half at the peptide bond that's C-terminal to the phenylalanine. And then, so one half of it can leave and the other half is stuck. I was like, I always think when I think of this, I think of this story about, I forget who the child is, but it's some child that is somehow related to someone I know, one of my mom's coworkers. And he got himself in he was a little boy and he got himself in a situation where he was like, Grandma, I'm duck. And so, like, I'm stuck, except I'm duck. And so I always think of this little boy when I see serine proteases because the peptide substrate is literally stuck to the protein. We have aspartate. Still pulling. Okay, so then that's R, but then we also have the C-terminus, the C-terminal half of that peptide. So this, so if we were to put, I guess if we go ahead, this is that nitrogen. That's right there. That's going to become the N-terminus of the new peptide. But then we're still stuck over here with the C-terminal or with the N-terminal half of the original peptide stuck in the active site. And what do we know about what enzymes have to look like at the end of a reaction? They have to look exactly the same, because if we don't return them, let's say that we found them, they can't catalyze the next reaction. We don't want there being any junk left in the active site. It has to look exactly like it looked when we started. So that means we have to get rid of that serine. By the way, on this step, what's histidine doing? What's its job there? So we saw up here, the histidine is acting as a general base. So what's going on down here? Okay, right? And so if abstracting a proton is being a general base, then what's donating a proton? It's general acid, right? So then histidine's acting as a general acid down here. So in all of these steps in the chymotrypsin mechanism, histidine was literally flip-flopping. And so this is why we did like 15 different exercises where I was like, what's the protonation state of histidine? Because histidine can flip-flop so easily like this because its pKa is 6. It's able to hang out in either a deprotonated or a protonated state. Yeah. Yeah. Try me. I'll try to answer it.
The role of aspartate is that hydrogen so that other nitrogen able to react.
The aspartate is making the histidine a stronger base. Okay. So sometimes when you see this mechanism, you won't even see the aspartate drawn in. And like there may be a situation with the protease, I have to look it up, but like there may be a situation with a protease where aspartate isn't even there. So like that mechanism I pulled up, like you didn't even see aspartate. It's just like histidine, because histidine's a general acid base. Hey Rupert, histidine's a general acid base, and then serine's a nucleophile. And like, yeah. Yeah, it's making histidine a better acid base guy thing. Okay. All right. So does anybody remember how we get the second half of the peptide freed from the active site? Oh, and this leaves. Bye. Okay. Anybody remember how we get the second half of the peptide disconnected from the active site of the serine protease? I was gonna say you're forming the words, Emily. Yeah, water. So we need something to act as a nucleophile that's not attached to the protein, and something that is a worse leaving group than serine. So it won't leave, and serine will leave instead. And fortunately, we talked about what's the concentration of water, guys? It's 56 molar. The concentration of water in water is 56 molar. So there's a lot of water around. So it's really easy for chymotrypsin to like grab a water molecule and have it in the active site to go and do chemistry. The second step we want to liberate, we've liberated the C terminus. So this being attached to the C terminus. We've liberated the C terminal half of the peptide. Now we need to liberate the N terminal half of the peptide, because we don't want the chymotrypsin to get a permanent attachment. We don't want it to get an extra appendage. We want it to be able to chew up more peptides. So the way that our body works around this is it pulls in water. Oh, let's draw that out nicely. Hashtag embarrassing. I should just do all my mechanisms on this program. It's so much nicer. Rupert, I was telling him about how my family decided that the time when I was doing my mechanism would be a good idea to have an in-depth conversation. And I had the conversation muted on my phone, but I enabled notifications on my watch. So my watch was like buzzing for like 3 minutes straight. And I'm like trying to write a mechanism. My phone was like, ah! And I'm like, is someone dying? Oh no, my sister just got new steel-toed boots at the plant. Okay, great. Okay, anyway. Okay, so now we have water here. So what's going to happen is histidine, again, we're making histidine a stronger base because the aspartate's pulling on it. So the histidine, the lone pair electrons on the histidine nitrogen are going to abstract a proton off of the water. So now water, like serine, you have a bunch of negative charge concentrate, a bunch of electron density concentrate on that oxygen, but the only thing that's attached to that oxygen is a proton. So like, it's not very happy. So it's going to want to either find a proton or attack something. And so in this case, the electron density is going to go and it's going to attack the carbonyl carbon. The electron density is going to go back up onto that oxygen. And how is that electron density able to even go up out of the oxygen in the first place? What does the enzyme do to enable that? It has the oxyanion hole. Whee! Oxyanion hole hanging up out there. Okay. So the oxyanion hole is like helping that happen. Okay. But as we know, okay, H, just going to be lazy. Serine, histidine. I was going to say, I heard you guys laughing with Dr. Macaulay today. Hopefully that's a good sign. Goodness, here we go. I like her. She's pretty cool. A minus. Okay, there we go. We're pulling on that nitrogen. Okay. All right. So there we go. So if we go back and we do the test, the logic test here, we know that the electron density can't hang out on that oxygen. So some of that electron density is going to have to collapse down and reform the double bond. So now let's go through and do the process of elimination here of what's going to leave. So is this bond going to break? Why will this be our leave? Is that a good leaving group? That second half of peptide? No, because we don't want a negative charge hanging out on the carbon. That's like a bad idea. That's not going to happen. What happens if we had water leave? Yeah, yes, Emily. Okay, what's going on? Thank you, Emily. Got it. Appreciate it. Thank you. Okay. Thank you. Keeping me honest. Okay. So what would happen if the OH left? The OH going to leave? Yeah, no, you're going to end up with the same thing again. So the water isn't going to leave. So the serine's going to leave. And the serine's going to leave because it turns out that both the hydroxyl and the other half of the peptide on their own, being the leaving group, not great. So by comparison, the deprotonated serine is going to be the best leaving group in this case. So that bond between the serine hydroxyl oxygen and the carbonyl carbon is going to break. Where's it going to find its proton? Yes, it's going to take the proton off of histidine. The charge will go back down on the histidine. And then what we'll end up with is our other half of the peptide is going to be free with a free carboxylic acid. And then we're going to have protonated serine. Deprotonated histidine. And then aspartate. Good old aspartate, who nobody really understands why it's there. Okay. All right. So that's our second product. All right. And then that is free to leave. And then the next peptide can come in and it can begin the process again. So popping back in this step right here. Okay. What is histidine acting as here in this step? So I guess let's say, okay, this is step one. Okay, this is step one. This is step two. This is step three. Whoops, 3 down here. And this is step 4. So it's step 3 where we have the histidine nitrogen abstracting a proton. What is histidine's job? What is it doing? Hint. We already said it for step 1. It's general acid. Nope. It's abstracting a proton. It's a general base. Now, down here, histidine turns around and donates that proton. Histidine's acting as a general acid down here. Okay. So this is accomplished through, first, we have a nucleophilic attack. And the nucleophilic attack is enabled by histidine acting as a general acid. Then we're going to see a tetrahedral carbon intermediate, although we haven't drawn it right there. It's acting as a tetrahedral carbon intermediate. There we go. And the tetrahedral carbon intermediate can happen because of the oxyanion hole. So Rupert, I was showing the class earlier before you came in that the active site of chymotrypsin actually has the backbone amines of glycine 193 and serine 195. It has the protons that are oriented, so it can hydrogen bond with a double bonded O, but it also helps stabilize the O- and the transition state / intermediate. Yeah, so that's the oxyanion hole, and that's what it looks like. And if you look at the mechanism that I uploaded, I drew it out with like lines. It was like oxyanion holes, it's there. But yeah, so the oxyanion hole helps that at least form and have a chance, but it's not going to last long. And so the electron density will collapse, and this is when the amide bond is going to break, and the nitrogen is going to leave. It's going to pluck a proton off of histidine. So histidine here, again, acting as a general acid. So the opposite of the dop adjusted. So this is, again, why we spent so much time learning about histidine, because histidine can flip-flop back and forth, and it's really important for enzyme mechanisms. You're going to see histidine a lot in enzymes for this reason. So none of y'all are taking 371L. Would any of you ever take 371L? Okay. Well, the catalytic amino acid in lactate dehydrogenase, which is the enzyme that uses, it's a histidine for this reason. Because depending on the pH, the protonation state of a histidine determines the direction of the reaction. So, okay. Oh, yes. Were you just, okay. Okay. So then it's stuck. This half, the right half or the C-terminal half of the peptide can leave, but the N-terminal half is still stuck. And we have the, I almost forgot. We have the acyl enzyme intermediate. And so the acyl enzyme intermediate happens after the C-terminal half of the peptide leaves, and then you have the serine covalently bound to the N-terminal half of the peptide. So this is our acyl enzyme intermediate, and this is where we see covalent catalysis is a thing, because temporarily our intermediate is covalently bound to the enzyme. Okay, so then after that happens, again, the enzyme needs a way to disattach the serine from the enzyme, because if we have it stuck there, the enzyme can't do a job for another reaction. So the enzyme is going to use water as a nucleophile for it. So the enzyme's going to get water to do its dirty work for it, because if it uses another amino acid, it's just going to get even more stuff. And we don't want that to happen. So water is deprotonated by histidine, so histidine acts as general base. The water makes a nucleophilic attack. We see our second tetrahedral carbon intermediate, and then we end up serine ends up leaving rather than the hydroxyl or the C-terminal half, because out of all those potential leaving groups, it happens to be the best. And so that's how we end up with our regenerated active site and the other half of the peptide that is then free to leave. That's one of the reasons why if we go back to the enzyme mechanism handout, I said, if you're a little bit confused, I know it's a lot of different things. If you can remember these steps as a guide, you have a nucleophilic attack, you see a tetrahedral carbon intermediate, then you see the acyl enzyme intermediate, water then acts as a nucleophile, and then along the way you're going to see a second tetrahedral carbon intermediate. These are the benchmarks that you should have in your mechanism that will help you know that you're following the right route. And again, the clue, one of the things I was saying in the beginning, Rupert, was, and you'll see an example of this on your quiz, and there's an example in the practice exam, is I'm going to give you an theoretical enzyme. I'm going to give you some characteristics about the enzymes, like maybe what amino acids are in the active site, and you should be able to look at the amino acids I give you, be able to kind of infer what the jobs of those are, and then be able to predict what the mechanism would look like based on which of the two enzyme examples we cover in class that it looks like. So like if you have a catalytic triad, I'm never going to just give you serine, histidine, and aspartate and be like, regurgitate it, right? But it might look like that. Or you might just get a serine or histidine, or maybe that aspartate could be a glutamate. Like they're going to be, enzymes evolve slightly differently, and based on the shape of the enzyme, the shape of their active site, those amino acids might change in identity, but you should be able to make that jump. Yes, Emily.
Would it be okay to write what amino acids?
Yes, this is okay for the quiz, yes, because they're not free-floating individual amino acids. They're amino acids that are part of a chain, but they're amino acids that aren't close together in space. So like if we look, so again, we'll actually see this on Thursday, but they're actually histidine 57, serine 195, and aspartate 102. So we're not anywhere close together in sequence, right? I mean, yeah, there's about 50 amino acids between. No. Yeah. They're far apart in sequence space, but they're close in proximity space. So you really couldn't even draw them like together because they're part. Yeah, they're not linked together. So yes. So yeah, just drawing it like that, I'm totally okay. So like, if I'm like draw a peptide, which you're not going to have to do for the enzyme quiz, but if I'm like draw a peptide, like yes, but if it's like you have to draw the active site residues, like that shorthand is perfectly acceptable. Good. All right. Any questions about the mechanism? Yes. Okay, so it was abstracting or plucking the proton and then leaving the electrons behind on the oxygen. The carbonyl carbon. Yep. And it's general acid, general base, because regular acid base is a small molecule. So if water wasn't making a nucleophilic attack there, water could also act as a base because it could abstract a proton from somewhere else. But it's not. It's going to do a nucleophilic attack instead. A general acid or a general base is when the acid or base is part of the protein itself. It's an amino acid within a protein. And again, that's why we talked about pKa's and we went through and we drew them and memorized them, is because we want to know if one of the applications, we want to know if and when amino acids are protonative, because that can determine what their job is within it. So, okay, so if a general base is abstracting a proton, what's a general acid going to do? So it's on the board.
So like from finding the O to the carbonyl carbon on there.
Yep. It doesn't look like it's donating, but it is donating the proton. And then if you want, I can, just to convince you that you should go on this. Shouldn't have to convince you to go on the Sakai site, but if we look, here we go. I made this last semester because I felt bad because my stuff looked like a train wreck. But there it is written out nicely. Oh, I added an extra carbon onto histidine. That's embarrassing. And then I drew the amino acids on top here and then flipped around the peptide. It doesn't matter. You can see here it's much nicer. The stabilizing, the general basing, the nucleophilic attack, electron density goes up. Oh yes. Oh no, I forgot to say this in class. An example of proximity and orientation. there's actually a phenylalanine binding pocket in the enzyme. Should probably go back and mention that at the beginning of class. But that is an example of proximity and orientation, is that the in addition to the oxyanion hole over here, the enzyme has like a hydrophobic pocket that the phenylalanine slides into. And that's actually how it recognizes and is able to chop, because the phenylalanine like goes into the coin slot and then it chops. Need to remember to talk about that on Thursday. Okay, yeah. And then, yeah, so I would highly recommend taking a look at this. I know it's a slightly different formalism than you're used to. It's drawn a little differently because it might be drawn upside down, but it's also like a lot more legible. So, yeah. Okay. All right, next question. Okay, I'm going to erase that equation because that Okay, all right. Next question. I'm totally cool with sitting and staring at you guys for playing cat videos, but I'm here. I will play weird old people videos that you don't get. I've stopped trying to relate to people about videos because nobody knows what I'm talking about. Yeah. Rate of diffusion. Good. Oh, that's such a good question. Okay. All right. That is a really good question. Okay, cool. All right. So if we go to an enzyme reaction, so we'll write out a generic enzyme reaction. Now I'm going to switch to hot pink because I like hot pink better. Okay. So we have E plus S. We draw our equilibrium arrows between E dot S because, again, that step is in equilibrium, but the whole reaction is not in equilibrium, just that first part. And then we have the rate determining step where we go to E plus P, and we're neglecting E dot P because it's very short-lived. Okay, so what does E plus S mean? Okay, so we're not interacting with each other. What does E dot S mean? Right. So if we have our enzyme and our substrate, the step that goes between enzyme and substrate floating around in solution, and for the enzyme, the substrate to pop into the enzyme pocket, these two have to run into each other, and the substrate has to actually go into and stick to the binding pocket. And so we use the process of the enzyme and the substrate floating together through space to find each other as diffusion. So if I am just me and I'm floating around willy-nilly, I'm diffusing through space. So you can think of like molecules floating through a solution, or if they're just going at like the maximum rate they can and not impeded by something, that's so the bigger a molecule is, the more viscous a solution is, the slower it will be diffusing. Okay? So this step, so we can also, so we call this the K1 and the K minus 1, but if you look in the enzyme literature, we also see these referred to as the K on and the K off, because it's the rate of the enzyme the substrate going onto the enzyme, and that's the rate of the substrate popping off of the enzyme. Okay, so what happens? What we said is for Michaelis-Menten kinetics to work out, we want the slow state. We want the slow step to be rate determining. Okay. However, that's not always the case. To make the math work out, we have to we have to assume that the K2 is the smallest step, but that's not always practically what happens. And sometimes the K is really, really big, or is really, really, really big, and so we have a really fast rate. And so what happens is an enzyme that's diffusion limited. This step is so fast that the K on becomes rate limiting. Or maybe it's maybe the K on is so fast, I can't remember. But if the chemistry step is so fast, it becomes slowed down by the rate at which the enzyme and substrate find each other in space and then come together and make a complex. So an enzyme that's diffusion limited, yes, the rate determining step is the enzyme and the substrate finding each other. And so with those types of enzymes, the diffusion limiting enzymes, what you can think of it as is the minute the substrate hits the enzyme, it's immediately turned over into the product and leaves. And so the slow step is the substrate and the product meandering through space, if that makes sense.
When would the slow step
The diffusion means. So there are enzymes that are diffusion limited, and so there's a limit. So for enzymes that are diffusion limited, you have a catalytic efficiency, or a Kcat over Km of 10 to the 8th to 10 to the 9th molar to the -1 seconds to the -1. So like in theory, if you calculate the catalytic efficiency of the enzyme and you get a value of around 10 to the 8, 10 to the 9, that's going to tell you it's diffusion limited because it's so efficient. Thanks for coming, Janelle. Because it's so efficient that the rate determining step is becoming diffusion. And so the ratio of the Kcat and the Km can help you get a ballpark for that. And there are different tests you can run to figure out whether or not it's diffusion limited, but that's one way that you could see it, and you could figure it out as in biochem class. Okay, but that was a really good question. So the catalytic efficiency, and I asked that question on the pre-example, in the pre-class assignment, and it's on the key. But the reason why we have the catalytic efficiency is because when we're comparing enzymes, we want to give enzymes equal playing ground, or we want to give enzymes a fair shot when we compare them to each other. So that's one reason why if we're comparing the speed of an enzyme, that's one reason why we use the Kcat instead of the Vmax, because the Vmax changes, it gets bigger with bigger enzyme concentration and smaller with smaller enzyme concentration. So using the Kcat instead of the Vmax allows you to correct for concentration. It also allows you to compare between enzymes. But some enzymes are really good at being fast, and some enzymes have a really low Km. And so we use the catalytic efficiency to help us figure out what's the most efficient enzyme. So like if you look at, on number 3, if you look at enzyme X, yeah, tough tits. If you look at enzyme X and enzyme Z, enzyme X has a Kcat of 1,000 per second and 10 micromolar. Enzyme Z has a Kcat of 100, but a Km of 0.5. So if you were to just look at the Kcat alone, oh, that doesn't tell you anything. If you were just looking at the Kcat alone, you'd be like, oh, enzyme X is better. If you were just looking at the Kn, you'd be like, oh, enzyme Z is better. But it's the combination of the relative strength of that binding interaction and then the velocity. It's the combination of the two that tell you how good an enzyme actually works. So you're never really going to see enzymes compared with their Vmax or their Km. You're going to see them compared with their Kcat over Km, if you want to make a head-to-head comparison over which is better. Yeah. Yes, Rashawn. Yes, and like it's hard to say. I was gonna say it's a little bit. I don't like using that or the strength of the affinity because it's kind of simplistic, because it's the amount of substrate that gives you half Vmax, so we're half of the maximum productive binding that leads to chemistry. But the way I think about it in my head is yes, the affinity, or it gives you the relative strength of the reaction. Yeah. So if we're thinking about in terms of an enzyme likes its substrate or doesn't like its substrate, which is better, a bigger or a smaller Km? Which is going to have a stronger, yeah. So it's the same with Kd. The smaller the Km, the more the enzyme likes the substrate. The bigger the Km, the less the enzyme likes the substrate. Pardon? So not necessarily. It just depends on the Km and the Kcat. So in theory, a smaller Km is better, but you don't want it to become too small because then it would hold onto it too tight. So if you were looking at them in isolation, you would say, well, a bigger Kcat is faster, and a smaller Km means there's a stronger interaction. A smaller Km means a stronger interaction, but the two, you can't make a definitive judgment. You could say, oh, that enzyme has a stronger affinity for that substrate, or that enzyme is faster, but you couldn't make a qualitative or a quantitative decision on whether one enzyme was better or more efficient than the other without looking at the two. All right, you heading out, Alex?
Thank you.
All right, thanks for coming. Okay. All right, next.
I think I just forgot, I didn't write it down on Thursday.
Sure.
We were doing
Sure.
the plots and such, and then using the equation of the line.
Mhm.
We go over what each part of the equation.
Of course.
corresponds to.
Yes, of course. And I have a figure for that. And again, all the PowerPoints are up and they're all labeled. And I put a key. I don't like to put in the keys for the problems because I don't like people to use that as a crutch for class. However, because we had so much going on the past couple of days and we had so many absences, I just went ahead and I posted it. Plus, I didn't tell you I was going to do it until after the fact, so it's fine. But okay, so if we look at enzyme here we go. Okay, I should have that nice plot. Do I? I'm gonna feel okay. I don't. That at least me to be a dick. Okay, enzyme. Okay, here we go. Okay, all right. So when we do that, so whenever you take the double reciprocal of something, so you take the 1 over the x and the 1 over the y, that's an old school trick for turning a curved line into a straight line. And we did this, and so it works really well for if you want to visually see what an inhibitor does. And honestly, if you have good data that don't have a lot of error in the measurement, Weinberg can work fine. In most cases, it's going to give you an answer that's within reason of the answer that you would get from a direct fit. However, what we saw, the example we saw from class is what happens is one of the reasons why Lineweaver-Burke isn't the preferred method, and that's because you have a tendency to have more error in your smaller values. And on a Lineweaver-Burke plot, your small values are all the way out here, and the values that are out here are going to have a higher effect on the slope, a bigger effect on the slope than the ones that are clustered down here. But again, Lineweaver-Burke, it's in terms of a straight line. So the x is 1 over s. The slope then is Km over V. Ooh, the Km, or the slope is Km over V max. And then the y-intercept, or the B, is 1 over V max. So what you can do with the Lineweaver-Burke is you can go back and the thing that I like to do first, and if I was walking you through it in class rather than having you do it in a group, what I would have said is the first thing I do is I always do 1 over B to solve for V max. And then you can multiply the slope by V max to solve for Km. So if you take Km over V max times V max, that gives you Km. And so that's like the foolproof method for going through and solving for Km and Vmax from a double reciprocal plot. But, so that's one way that if I gave you graph data, you could go in and you could be like, okay, if Dr. GB just gave me a data table, she wants me to do a Lyman-Burke plot, that's what you do. Or I could give you a set of data and give you an equation. And then you could go in and from the equation, you could figure that out. Similarly, if we were to look at a direct fit, look at a hyperbolic equation, you could, if I gave you an equation, the Vmax is the coefficient on top, and the Km is the coefficient on the bottom of the hyperbola. Similarly, you could estimate it from looking at where the hyperbola levels off. And then from the Km, you can do find the half Vmax and then go down to the substrate on the X. That's how you could get data from either type of plot. And again, these days, I think Dr. Arnett may have the students download sigma plot and do a direct fit. I don't make you do that, but I like you to know that you can do it. Just because things get complicated, sigma plot's only on PC and not everyone has a PC, and I just don't want to deal with that. I had to deal with that in 371L, and that was enough. So you can just trust me that there exists graphing software out there where you can do that. Yeah, and that's the preferred way. But yeah, but I admittedly shat on Lyman-Burke quite a bit on Thursday, but I was more so proving a point of why you have to be careful whenever you try to linearize curve data. And for years, I always said that you won't get data, you won't get enzyme data into a publication with Lyman-Burke. Yeah, you totally can. And I was like, really? Okay. They don't have that software where you are? Okay. So you can't download a free trial? Okay, fine. So yeah, anyway. Why we're lucky to be at a university that can afford to buy us a universal subscription. Okay, next question before I go into Rantland. Did that help?
Yeah.
Okay.
Yeah. No, I just noticed.
Yeah. Yeah.
I'm kind of curious about what other organic chemistry techniques you would need to know, or I guess like the drug mechanisms or anything else about organic chemistry to provide the field of like.
So there's going to be some mechanisms. So okay. So honestly, really, so last semester I had my advisor come in and briefly to my class. And what he told my class was that in biochemistry, 95% of the time is going to be an amine attacking a carbonyl. Most of the chemistry that we're going to see in biochem is going to come from something attacking a carbonyl carbon. And in this case, for the mechanisms that we're going to be doing right now, there's two options. It's going to be an amino acid. And so it's probably going to be an amino acid that's going to have an atom on the end that can tolerate a negative charge and can act as a nucleophile. Or it's going to be water. And the amino acid that's going to be in your active site is going to be deprotonating water and having water do its dirty work for it, because for whatever reason, the amino acids that you have in the active site can't act as a nucleophile. And so we're going to see with the HIV protease on Thursday that the HIV protease has two aspartates. And aspartate doesn't necessarily, it can in theory act as a nucleophile in the right situations, but you're not going to see aspartate act as a nucleophile to a big peptide in the active site. And so instead, with aspartate proteases, you're going to see aspartate just deprotonating water and acting like it did, seeing like the steps 3 and 4 of the serine protease mechanism. Now, when we go into nucleic acid chemistry, so I don't think we're going to be doing any, there may be a mechanism or two for carbohydrates. I think we may look at the dephosphorylase mechanism, but I can't remember off the top of my head. For nucleic acids, we're going to be doing a little bit of chemistry, but it's literally going to be attacking phosphodiesterase. It's going to be breaking and making phosphodiester bonds. So instead of attacking a carbonyl phosphate or carbon, you're going to be attacking a carbonyl phosphorus. And so it's going to be the same up, down, what leaves over and over and over again. It's just going to look a little bit different. So if you can get that you need to have something nucleophilic, you can figure out whether or not something has the electronic and like the lack of bulk factor to be a nucleophile. Can it be attacking? And then will it attack? Can it leave? And then recognizing what's a good electrophile. And for the purpose of this class, the thing that's always going to be attacked is going to be either a carbonyl, a carbon double bonded O, or it's going to be a phosphate, a phosphorus double bound to an O. It's going to be one of those two things. And again, thinking ahead, glycolysis, we may get a little more creative with glycolysis, but with glycolysis mechanisms, that's going to be more being like, that's going to be more of a regurgitative mechanism kind of a thing with glycolysis. But for this, I'm interested that you can know enough about the amino acids to predict how certain amino acids in an active site would act, if that makes sense. Okay, but yeah.
When you were mentioning water in an active site, you said water will become deprotonated by what?
An aspartate.
Okay, and that's kind of like a general constant, or just for the.
So that's for HIV protease, but you could see a situation where maybe it's not an aspartate, maybe it's a different amino acid, but it's going to be deprotonating water. Well, if we deprotonate water and you have a carbonyl hanging out, what's going to happen? But another thing too is also to remember, if you get lost, also think about what you want your products to be too, and that can help orient you to where you should be attacking. Sometimes it might help to like draw in and highlight which of the bonds you want to break, and that can help you figure out where to attack. Okay. All right. Next question. No questions too silly. I mean, in theory, we could also go over problems if you guys wanted, but do you guys have any book problems or anything that were interesting to you? Do you want to go over any kinetic concepts or? Pardon? Gotcha. Are any questions about hemoglobin? Don't let my knitting intimidate you. I'm listening. Oh, helical wheel. Goodness, someone had a banana out today, and I was thinking in my head, I was like, are you gonna make it out the helix? No. I actually used a toothpick yesterday to test the doneness of my cake, and I was like, oh, class. Okay. So do you guys have a favorite amino acid? You already know my favorite amino acid. My favorite's arginine. It's so complicated.
I only have least favorite.
What's your least favorite? Tryptophan. Yeah. As you can see, as I've like failed to draw histidine in class a couple times. Yeah, histidine. And like you remember there's two nitrogens, and one of them's protonated and one of them's deprotonated at pH 7, and the one that's deprotonated has a double bond, and the one that's protonated doesn't, but I always like get them messed up on their relative placements on the ring. Yeah. Yeah. So I always have to stop myself and be like, okay, where is it?
Before the amino acids, because I was having like stress dreams, and like in my sleep, I remember being like, Arginine, which one is that? And then I would try to think of it in my sleep, and then it would come to mind. I was asleep.
Oh goodness, I was gonna say, okay, I should probably. Okay, I'm gonna disconnect this for a second. We're gonna go. I was gonna say, we'll take a trip to Fun Town for a second. Or no, you guys are, or you. It looks like you may be packing up. But let me really quick see if I can find this picture that I drew. I've got some pictures from when I was learning biochemistry. I used to, back before grad school killed my soul, I used to make doodles about chemistry. I can't remember if I had them on my Facebook. Let's see. I'm pretty sure I did. And then when I came and gave a seminar at my college as a grad student, my advisor like whipped out this sheet of cartoons I had made. It was really embarrassing. Okay, yeah, here they are. Okay, where is it? Oh no! Oh no, I didn't do one. Oh yeah, okay. Yeah, okay. Here we go. This now it doesn't look nearly as funny and cute as I remember it. Doesn't look nearly as funny. It probably won't mean anything to anyone. That's okay. Yeah. Yeah, okay. I was telling my English major roommate that I liked arginine because of a pirate joke, and I made a cartoon of it. What else did I have here? Oh yeah, yeah. Oh goodness, these are fun times. Oh yeah, that was me and my friends getting chased by a DNA monster. Oh yeah, that was the time I imagined. That was when we were doing carbohydrates, and I was pretending that a glucose was a swim float. It's so crazy. Oh, Grignard reactions. Oh my goodness. Did you guys ever have to do Grignard reactions? Yeah, didn't work. Too humid, didn't work. Solvent evaporate, 5% yield, didn't. Yeah. Oh gosh. Oh yeah. That was back when I used to get anniversary mugs from the American Chemical Society before I waited too long to renew, so they stopped giving me mugs. Oh yeah. Goodness. Oh yeah, I used to put model kits on my head and call it a crown. Science. I was my point, I was definitely delirious as a chemistry undergrad too. It's fine. None of y'all are chemistry majors, right? No. I was a chemistry major, and I was like, this stuff like still drove me crazy. So it's fine. That's how I coped. I actually have like a binder. I don't draw cartoons anymore. But one of my friends, she's in grad school. I should probably ask her if she's defended yet. But she's getting her PhD in British literature in England, and she has a notebook of all my comics. No science ones for her, but anyway. Okay, sorry. You guys look like you want to leave, so. That's how I started. It made me so there's two types of domains of learning. There's the one where it's like the knowledge domain, and I can't remember what that's called. Then there's the affective domain. And the affective domain is like how you emotionally feel about the material. And it's not directly like related influencing with like what you learn, but it just makes you feel better about learning. And so for me, like making comics definitely helped with my affective domain. It made me feel better about what I was doing. So yeah. Okay. So are you guys questioned out? You guys chemistry'd out? Okay. So no interest in me pulling out the book and doing some problems? Okay. Okay. All right. Awesome. I'm totally cool with that.